Metallic bonds. Metallic bonds. Metals have specified properties. These are good conductor of heat and electricity. Metals are good conductor of heat and electricity. That means the electrons is easily provided in a conductor. Okay. The high conductivity in metal is due to presence of mobile electrons. Presence of mobile electrons which move from one place to another in the electric field. In the electric field. Okay. The high conductivity in metals. The high conductivity in metals is due to the presence of mobile electrons which move from one place to another in the electric field. Okay. These are malleable and ductile. These are malleable and ductile. These are malleable and ductile. These are opaque, have a reflecting power. These are opaque and have high reflecting power. Okay. Their melting and boiling point are also very high. Their melting and boiling point are also very high. Points are also very high. Okay. They emit electrons at high temperature. They emit electrons at high temperature. Okay. The coordination number is either 8, 12 and 14 in their crystal. The coordination number is either 8, 12 or 14 in their crystal. Okay. These properties of metals cannot be explained with the help of simple ionic or covalent bond. Okay. This property of metals cannot be explained with the help of simple ionic or covalent bond, since all the atoms of metals are same, hence these are not held together by ionic bonds, because ionic bond is formed between atoms of different electronegativity. The metallic crystal possesses considerable strength, as the forces operating between the metallic atoms must be greater than van der Waals forces, as coordination number is very high at 12 and 14. Therefore, atoms in metallic elements cannot be held by covalent bonds. because they do not have many electrons in their valence shell. Okay? Hence, a special type of metallic bond must be considered. Thus, the cohesive force due to which atoms of metals bind together in metallic crystal is called the metallic bonds. Okay? Then metallic bonds, the cohesive force due to which atoms of metals bind together in metallic crystals is called as metallic bond. Or metallic bond is defined as the peculiar type of bonding which holds the atoms together in metals is known as metallic bonding, is known as metallic bonding. Okay, there are three main theories which explain the nature of metallic bond. These are three main theories. There are three main theories which explain the nature of the metallic bond. Okay. First, FET, free electron theory or electron pool gas theory. FET, free electron theory. Or electron pool gas theory. Second is valence bond theory, VBT, valence bond theory, VBT, or resonance. Third is molecular orbital theory, MOT. Molecular orbital theory or bond theory. bond theory. Bond theory. First, free electron theory, FET. Free electron theory, FET. Free electron theory, FET. Electron pool gas theory. Electron pool gas theory. Electron pool gas theory. Okay. This theory was first proposed by Drude in 1900. Okay. This theory was first proposed by Drude in 1900 and was developed by Lorentz in 1923. This is also called Drude-Lorentz theory. This is also called Drude-Lorentz theory. Okay. Drude regarded a metal as a lattice with electrons moving through it in the same way as molecules of a gas are free to move. Lorentz later on suggested that metal comprise a lattice of rigid sphere positive ions embedded in a gas of free valence electrons which could move in the interstices. Okay? Interstices. As the ionization energies of metals are low, they easily lose the valence electron to form the metal ions known as positive cores or kernels. The electrons now no longer belong to any individual metal atom but to the crystal as a whole. The cation remains fixed in the crystal lattice. Hence, according to this theory, the metallic solid may be visualized as the cation submerged in a sea of electrons. Okay? In a sea of electrons. Okay? Free electrons is called metallic bond. Free electrons theory can be explained many properties of metals. Metallic luster. Free electron theory can explain many properties of the metals. Many properties of the metals. First, metallic luster. Okay, first is metallic luster. When a beam of light falls on the surface of the metals, the mobile electrons get excited. When these electrons come back from the excited state to the ground state, the rays of all wavelengths are emitted, which lies in the visual region. So when the light falls on the metals, it appears that the reflection takes place and the surface seems to be bright. Therefore, the surface emits the typical metallic luster. Okay? When a beam of light falls on the surface of the metals, the mobile electrons get excited. The mobile electrons get excited. When these electrons come back when these electrons come back, when these electrons come back from the excited state to the ground state, from the excited state to the ground state, the range of all wavelengths, the range of all wavelengths are emitted which lie in the visible region, So when light falls on the metal, light falls on the metals, it appears that the reflection takes place. Reflection takes place. Reflection takes place, and the surface seems to be bright. Therefore, the surface emits the typical metallic luster. Therefore, the surface emits the typical metallic luster. Next is electrical conductivity. Second is electrical conductivity. High electric conductivity is due to the presence of mobile valence electron. Due to the effect of imposed electrical field, these loosely bound electrons move from one place to other in the crystal lattice, and the electron C serves as a carrier of the electricity. Okay, high electric conductivity is due to the presence of mobile valence electrons, due to the effect of imposed electrical field these loosely bound electrons move from one place to other, in the crystal to other in the crystal, lattice and the electron, she serves as a carrier of electricity. Okay. Next, first is metallic cluster, second is electrical conductivity, third is thermal conductivity. Thermal conductivity. Third is thermal conductivity. Thermal conductivity of metals is due to free movement of the electrons. When heat is applied to any site of crystal lattice, the cations obtain a high kinetic energy. Cations having high kinetic energy transmit some energy to mobile electrons, which in turn transfer energy to another neighboring electrons. In this way, the heat is transmitted from one end to the other in the metals. Okay? Thermal conductivity of metals. Thermal conductivity of metals is due to free movement of the electrons. Free movement of the electrons when heat is applied to any site. When heat is applied to any site, when it is applied to any site of the crystal lattice, the cation obtained high kinetic energy. Cations having high kinetic energy. Cations having high kinetic energy transmit some energy to mobile electrons. Which in terms of electrons, transfer energy to another neighboring electrons. Neighboring electrons okay. In this way the heat is transmitted from one end to other in the metals. Okay. Thermal conductivity of metals is due to free movement of the electrons. When heat is applied to any site of the crystal lattice, the cations obtain a high kinetic energy. Cations having high kinetic energy transmit some energy to mobile electrons, which in turn transfer energy to another neighboring electron. In this way, the heat is transmitted from one end to the other in the metals. Okay. Next is malleability and ductility. Next is malleability and ductility. Okay. Fourth point. Fourth point, malleability and ductility. Melting and boiling points. Fourth point, melting and boiling points. Due to non-directional property of a metal, non-directional property of a metal bond, strong electrostatic forces of attraction between the positively charged metal ions and the nearby mobile electrons. Those metal process high melting and boiling point. Those metal process high melting and boiling point. Okay, melting and boiling point. Due to non-directional property of a metal bond, strong electrostatic forces of attraction between the positively charged metals ions and the nearby mobile electrons. Thus metal process high melting and boiling point. Next is malleability and ductility. Fifth is malleability and ductility. Next is malleability and ductility. Okay. Malleability and ductility. The metallic bond holding the positive ions and the valence electron is non-directional. There are no localized bonds. The bond holding the crystal lattice in metals are not rigid as in covalent solids. The result is that cations can be easily moved from one lattice side to another. Okay? One lattice side to another. There are no localized bonds. The bond holding the crystal lattice in metal are not rigid as in covalent solids. The result is that cations can be easily moved from one lattice side to another. Hence, an application of mechanical force, one plane of cations can slip over the other plane in the crystal lattice. Since the delocalized electrons are available everywhere, so the relative position of the cations do not change even in application of mechanical forces. The nearest kernel can easily be changed, and new metallic bond can also be formed easily due to age of slipping over and new bond formation. The metallic crystal can be beaten and their wires can be easily drawn. Okay? An application of a mechanical force on application of mechanical force, one plane of cations force one plane of cations can slip over the other plane in the crystal lattice. Since the delocalized electrons are available everywhere. Okay? So the relative positions of the cations, the relative position of cations do not change even an application of mechanical force of mechanical force the nearest kernel can easily be changed and a new metallic bond can also be formed easily. Due to their wires can be easily drawn. Okay? Next is elasticity. Elasticity. What is elasticity? Okay? Elasticity is the property by virtue of which a substance can recover its original form soon after the removal of the deforming force. The cations can change positive without breaking the metallic crystal, shows that under mechanical force the structure is temporarily changed and it attains original position and withdrawing the applied force. Okay? Elasticity is a property. Elasticity. Elasticity is a property. Elasticity is a property by virtue. Elasticity is a property by virtue of which a substance can recover its original form. Its original form soon after the removal of the deforming force. The removal of the deforming force. Removal of the deforming force. Okay? The cation can change position. The cation can change position without breaking. Without breaking the metallic crystal. The metallic crystal shows that under mechanical force. Stress. The structure is temporarily changed. The structure is temporarily changed. And it attains the original position and withdrawing the applied force and withdrawing the applied force. Okay? Next is resonance or valence bond theory VVT. Next is resonance or valence bond theory VVT. Valence bond theory VVT. Regarding metallic bonds, second theory was proposed by Pauling. According to this theory, metallic bond is basically covalent in nature and metallic structure have resonating electron pair bond between any atom and its near neighbors. Okay? Regarding metallic bonds, VVT. Regarding metallic bonds, second theory was proposed by Pauling. According to this theory, metallic bond is basically covalent in nature. And metallic structures have resonating electron pairs bond between any atom and its near neighboring. Okay? For example, X-ray study shows that an atom of lithium is surrounded by 8 lithium atoms. So coordination number 8. The electronic configuration of lithium is given as the electronic configuration of lithium is given as 1s2, 2s1, 2p0. The vacant 2p orbital, the vacant 2p orbital can form lithium negative by accepting an electrons by accepting an electrons lithium negative ion 1s2 2s1 2p x1 lithium positive ion 1s2 2s0. Okay, lithium bond can also be formed by sharing of electrons different resonating contributing structures of lithium metals can be written as lithium first arrow marker lithium this is second arrow marker lithium positive ion lithium negative ions arrow marker lithium positive ions lithium negative ions lithium arrow marker this is a third figure, this is fourth figure, and lithium negative ions lithium positive ions lithium positive ions arrow marker lithium negative ions lithium positive ions. Okay, lithium negative is linked with two covalent bonds. Lithium negative is linked with two covalent bonds. These are resonating covalent bonds. As to form such resonating structure, the metals must have vacant orbitals and their energies must not differ much. Vacant 2py 2pz orbitals accept conducting electrons, which explains the conductivity of the metals. The main drawback of BBT is that it does not explain the metallic character in liquid state or in solution. Okay, the main drawback of BBT is that it does not explain the metallic character in liquid state or in solution. Okay. Next, molecular orbital theory, MOT or bond theory. Molecular orbital theory. Next is molecular orbital theory. Next is molecular orbital theory. MOT or bond theory or bond theory. Molecular orbital theory. What is molecular orbital theory? Okay? Molecular orbital theory. This theory is similar to molecular orbital theory of covalent bond. The electrons in the metal are considered to belong to the crystal as a whole and are not localized between any two atoms. Hence, the metallic bond is formed by the delocalization of all orbitals containing free electrons. According to molecular orbital theory, when two atomic orbitals combines two molecular orbitals are formed. One of these molecular orbitals is of lower energy and is known as bonding molecular orbital (BMO), while the other is of higher energy and is known as anti-bonding molecular orbital (ABMO). Thus, for NaO atomic orbitals, n by 2 bonding molecular orbitals and n by 2 anti-bonding molecular orbitals are found in the metallic crystal. The value of n may be supposed in the order of 6 multiplied 10 to the power 23, where n Avogadro number. Hence, there would be 3 into 10 to the power 23, 3 into 10 to the power 23 BMO and 3 into 10 to the power 23 ABMO. Anti-bonding molecular orbitals. Okay? ABMO. The energy gaps between these MO are so close. The energy gaps between these molecular orbitals are so close that molecular orbital looks like a continuous bond. This is also known as quasi-continuous energy bond. So molecular orbital theory is called bond theory. This theory can be illustrated by taking an example of lithium. Okay, the molecular orbital theory is formed from one orbitals are completely filled. Hence, 1s bond is a non-conducting bond. When two lithium metals combine, the lithium molecule is formed. The 2s atomic orbitals in each of the two lithium atoms combine to form two molecular orbitals. One is bonding and another is anti-bonding molecular orbital. This valence electron occupied by bonding molecular orbitals. You can show with the help of examples. Okay? First A, lithium. That is 2s, one atom, lithium atom, 1, that is 2s atom, 2 atomic orbital, okay? That is anti-bonding and that is bonding. In case of lithium 3, in case of lithium 3, the shape of the molecular orbital, will be as shown below. B. 2s atom. First, 2s atom. Second, 2s atom. Third, that is anti-bonding, one. That is non-bonding, third. Bonding. Okay? With lithium and metal. Okay? 2s atom 1. 2s atom n. Many atoms n. That is many closely spaced molecular orbitals levels constituting a bond. Okay? Constituting a bond. Okay? In n atoms of lithium metals are allowed to combine to form lithium crystal, then three types of energy bond will be obtained. Okay? First is 1s bond. Okay? This bond is formed when n 1s atomic orbitals of n lithium atoms combine to form n energy levels which are completely filled. 1s bond is non-conducting bond. Conducting bond. Second, 2s bond. It is called valence bond as 2s are the valence energy levels, since each lithium atom contains only 2s orbital, and lithium atoms in lithium n metals have n levels in 2s band. Since the maximum capacity of n levels of 2s bond is 2n electrons, thus 2s bond is half filled. The upper half of this bond is empty while the lower half is completely filled. The completely filled levels of 2s bond and are very close to each other, so the electrons from the lower half can go to the upper half by energy available at normal temperature. Thus, 2s bond is called conduction bond. Okay, third point. 2p bond. Okay, third point, 2p bond. It is vacant bond. Okay. Since 2s and 2p levels are very close in energy, 2s and 2p bond overlap. The portion where 2s and 2p bond overlap is called overlap zone. The electron energy bands where the electron can move are called the permutated bonds. Two permutate bonds are separated from each other by empty bonds, which are called forbidden zones or forbidden energy gap. Different energy bonds of lithium crystal has been, we can show, okay, and the molecular orbital theory successful explain electrical, magnetical, conductivity, non-conductivity and semiconductor in metals. Okay? The molecules last. The molecular orbital theory, the molecular orbital theory successful successfully explains electrical, magnetic, conductivity, conductivity, non-conductivity, and semiconductivity in metals. Okay. The molecular orbital theory successfully explains electrical, magnetic conductivity, and non-conductivity or semiconductivity in metals. Okay. Next, band theory and physical properties of metals. Theory and physical properties of metals. Okay. With the help of bond theory, we can easily explain why some solids are good conductors, metals of electricity, and some are non-conductors, are insulator, non-metals, are semiconductors, semi-metals. Okay. First point. Generally, we may know also about conductor, but generally metals are good conductors of heat and electricity. Metals are good conductors of heat and electricity. Okay. Those materials which contain plenty of electrons for electric conduction are called conductors. The conductivity of the metals can be explained with the help of theory. The conduction band is partially filled and partially vacant. The electron can be transferred into this vacant energy levels due to electrical and thermal energies. This is why metal are good conductors of heat and electricity. Okay. You may know how to conductor is a good conductor. This is 2p. This is 2p, and this is 2p. N equals N 2p. Orbital of N lithium atoms. Okay. N lithium atoms. Okay. This is a vacant 2p bond. This is vacant 2p bond. Okay. This is vacant. This is vacant. This is vacant 2p bond. Vacant 2p bond. Okay. And after some time, this is vacant upper half band. Vacant upper half band. This is a vacant upper band. Okay. This is vacant upper band. 2s. This is 2x, 2s, and this is 2s. And by n 2s orbitals of n lithium atoms. N lithium atoms. N lithium atoms. Okay? N lithium atoms. This is N2s orbitals. So N lithium atoms. Lithium atoms. Okay? This is vacant upper half band. This is vacant upper half band. Vacant upper half band. This is vacant upper half band. Completely filled lower half band. This is completely filled. This is completely filled. This is completely filled lower half band. This is completely filled lower half band. Okay, half filled, and this is half filled 2s band conduction band. This is a half filled 2s band conduction band. This is a half filled. This is half filled 2s band and conduction band. Okay, conduction band. And this is a forbidden gap. This is forbidden gap. Forbidden zone. This is forbidden zone, and this is forbidden zone, and okay, this is forbidden zone, and this is 1s. This is 1s orbitals of this is 1s orbitals of n lithium atoms. Okay, this is completely filled. This is completely filled. This is completely filled. 1s band, non-conduction band. Okay, this is completely filled non-conduction band. Okay, then this is the formation of 1s, 2s, and 2p energy bonds in lithium crystal. Okay, lithium crystal. Okay, second, non-conduction or insulation band. Okay, non-conduction or insulator band. In non-conduction conductors or insulator, the valence band is completely filled. The valence band is completely filled. There is an appreciable difference in energy band gap between the valence band and the next empty bands. Okay? Hence, electrons cannot be promoted to an empty box where they could not move freely. This explains the non-conductivity of non-metals. Okay? Next is semiconductors. Next is semiconductors. Okay? Next is semiconductors. One. Conductors. 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 Generally, metals are good conductors. Generally, metals are good conductors, good conductors of heat and electricity, of good conductors of heat and electricity, good conductors of heat and electricity. Those materials which contain those materials which contain plenty of electrons, for electric conduction are called conductors. Okay? The conductivity of the metals, the conductivity of the metals can be explained with the help of this theory, with the help of band theory, okay? And help of band theory. The conduction band is partially filled. The conduction band is partially filled and partially vacant, and partially vacant. The electrons can be transferred. Into this vacant energy. Okay? Energy levels due to electrical and thermal energy. Okay? This is why metals are good conductors of heat and electricity. This is why metals are good conductors. Metals are good conductors of heat and electricity. Heat and electricity. Okay. Next, second point. Second point, non-conductors. Non-conductors. Non-conductors are insulators. Are insulators. Non-conductors are insulators. Okay. In non-conductors are insulators. Are non-conductors. In non-conductors. Non-conductors are insulators. Are insulators. Non-metals. The valence band is completely filled. The valence band is completely filled. The valence band is completely. The valence band is completely filled. Okay. The valence band is completely filled. Valence band is completely filled. Okay. There is an appreciable difference in energy. There is an appreciable difference in energy. Difference in energy. Band gap. Energy band gap. Okay. Between the valence band and the between the valence band and the next empty band. Hence electrons cannot be promoted. Electrons cannot be promoted to an empty level. Where they could move freely. That explains the non-conductivity. Explains the non-conductivity of non-metals. Okay. Next, third point, semiconductors. Semiconductors. Third is semiconductor. What is semiconductors? Okay. Semiconductors are those materials whose electrical properties lie between those of insulators and good conductors. Example, germanium and silicon. The substances in which electric conduction is not possible at low temperature, but on increasing the temperature electric conduction is possible, are called semiconductors. Semiconductors are solids where there is only a small difference in energy, known as band gap, between the filled valence band of electrons and conduction band. Okay. Semiconductors are those materials. Semiconductors are those materials. Semiconductors are those materials whose electrical properties Electrical properties. Whose electrical properties lie between those of insulators, and good conductors, and good conductors, okay. Good conductors lie between those of insulator and good conductors. Example: germanium and silicons. Okay. The substance in which electric conduction is not possible. Electric conduction is not possible. Electric conduction is not possible at low temperatures. But on increasing the temperatures, electric conduction is possible. Electric conduction is possible. Electric conduction is possible. Okay, are called semiconductors. Okay, semiconductors are solids. Semiconductors are solids where there is only a small difference in energy. Known as band gap. Okay, between the field valence band, of electrons and a conduction band. Okay, conduction band. Types of semiconductors. Types of semiconductors. Okay, there are two types of semiconductors. First is intrinsic semiconductors. And the second is extrinsic semiconductors. Okay. First, intrinsic semiconductors. Okay. Extremely pure silicon and germanium. Silicon or germanium is a material which is poor conductor of electricity. Electricity at a normal temperature. at a normal temperature, at a normal temperatures. Okay, the conductivity increases, the conductivity increases, the conductivity increases with increase in temperature, with increase in temperature, increase in temperature. Okay, these have field valence bond, these have field valence bond, these have field valence bond, non-conduction bond, non-conduction bond, and empty conduction band, and empty conduction band, okay. The forbidden energy gap is very less. The forbidden energy gap, is very less, energy forbidden gap is very less, small, okay. And that RT many electrons from the field valence band jump to the valence conduction band, and that at RT many electrons from the field valence band jump to the vacant conduction band, vacant conduction band. This indicates low thermal. Low thermal conductivity. Okay. Intrinsic semiconductor. Extremely pure silicon and germanium is a material which is poor conductors of electricity at a normal temperature. The conductivity increases with increase in temperature. These have a field valence band, non-conduction band, and empty conduction band. The forbidden energy gap is very less, small, that at RT many electrons from the field valence band jump to the vacant conduction band. This indicates low thermal conductivity. Okay, at low temperature, the energy is not sufficient to cross the forbidden zone, and these are poor conductors of electricity. Okay, at low temperatures, the energy is not sufficient. The energy is not sufficient to cross the forbidden zone. Hence, these are poor conductors of electricity. These are poor conductors. These are poor conductors of electricity. of electricity. These are poor conductors of electricity. Okay. On increasing temperature, on increasing temperature, on increasing temperature, on increasing temperature, the energy of electrons becomes sufficient to cross the on increasing temperature. The energy of electrons, the energy of electrons become sufficient to cross the forbidden zone, to cross the forbidden zone, to cross the forbidden zone. Hence some more electrons, and some more electrons jump to the conduction band. Jump to the conduction band. Thus the increasing temperature increases the electrical conductivity. Increases the electrical conductivity. Energy band diagram for intrinsic semiconductor. You can show what energy band diagram. Okay. Energy band diagram for temperatures. Energy band diagram. Energy band diagram. Okay, this is band energy. This is band energy. This is band energy. Okay, this is band energy, and this is empty conduction band. This is empty conduction band. One minute. Empty conduction band, and electrons jump from vacant valence band, and this is electrons jumped from valence band, and energy gap. This is Fermi level. And energy gap. This is energy gap is small. Energy gap is small, and this is energy gap is small, and this is positive. Okay, this is positively charged holes. This is positively charged holes. And this is filled valence band, and this is filled balanced band, balanced bond. This is field valence bond, non-conduction bond, non-conduction bond, conduction bond, okay, non-conduction bond, and this is energy band diagram. This is energy band diagram, energy band diagram, energy band diagram for an intrinsic, semiconductor at room temperature, okay, RT, room temperature RT, okay. Next is extrinsic semiconductors. What is extrinsic semiconductors? We will be knowing about extrinsic semiconductors, okay. Second is extrinsic semiconductors, okay. Extrinsic semiconductors, okay. What is extrinsic semiconductors? The substances which are normally insulators can sometimes become semiconductors when a small amount of impurities are added to them. Such substances are called extrinsic semiconductors depending upon the nature of impurity added. There are two types: N-type extrinsic semiconductors and P-type semiconductors. Okay, extrinsic semiconductors. The substances which are normally insulators can sometimes become semiconductors, become semiconductors when a small amount of impurities are added to them, such substances are called extrinsic semiconductors. Extrinsic semiconductors, depending on the nature of impurity. Depending on the nature of impurity, okay. Impurity added. These are two types. First is N-type extrinsic semiconductors, and B is P-type extrinsic semiconductors, okay. Extrinsic semiconductors. First, we will be knowing about N-type semiconductors, okay. N-type extrinsic semiconductors. These are obtained when an impurity atom to be added has more valence electrons than the parent insulators. This type of semiconductor is obtained by the addition of phosphorus, arsenic, or SB bismuth, SB bismuth 5 valence electrons to pure silicon and germanium 4 valence electrons. There are many extra electrons in the lattice point of arsenic as there are arsenic atoms. Crystals of germanium are semiconductors due to presence of extra electrons in the donor impurities. In this type, electrical conductivity is possible at high temperature because the field impurities levels of phosphorus, arsenic, bismuth are located near to the conduction band of silicon or germanium. The name N-type indicates the electrical conductivity is due to negatively charged electrons. N stands for negatively charged electrons. Each arsenic atoms okay. N stands for negatively charged electrons. Each arsenic atom forms 4 covalent bonds with surrounding 4 germanium atoms by using its 4 valence electrons and its 5th electron in left. Okay? Unused. Thus, there is an extra electron which is negatively charged. Hence, the name given as N-type, P-type, N-type. Okay? And P-type extrinsic semiconductors, these are obtained when an impurity atoms to be added as less valence electrons than the parent insulator. This type of semiconductor is obtained by the addition of boron, aluminum, or gallium. Okay, 3 valence electrons to pure silicon or germanium, 4 valence electrons. In this type, 3 valence electrons of each boron or aluminum form 3 covalent bonds with 3 germanium atoms, and the 4th germanium atom is linked with boron containing only 1 electron from germanium, due to which positively holes produced on increasing temperature electrons from silicon or germanium are excited to the impurity levels of boron or aluminum, and thus positive holes also produced. As electrons move into these positive holes, they visualize to migrate. Hence, in this type of conduction, is due to the migration of the positive holes, and hence the name of P-type has been given. P is used for positive holes. Semiconductors is also explained in the chapter under impurity defect, crystal defect. Okay? Semiconductors is also explained in this chapter under impurity defect, crystal defects. Okay? Next, difference between metallic and covalent bonds. Differences between metallic and covalent bonds. Metallic bonds, covalent bonds. The cohesive force due to which atoms of metals bind together in metals is called metallic bond. The bond formed by the sharing of electrons is called covalent bond. Second, this type of bond has non-directional characteristics. This type of bond has non-directional characteristics. Okay, and in covalent bond, this type of bond has directional characteristics. This type of bond has directional characteristics. Okay, characteristics. Okay. Third point, Metal are good conductors of heat and electricity. Metal are metals are good conductors. Good conductors. Metal are good conductors of heat and electricity. Electricity. Covalent compounds are bad conductors. Covalent compounds are bad conductor are bad conductors of heat and electricity. Okay, electricity. Graphite is an exception which is good conductor. Graphite is an exception. Graphite is an exception which is good conductors. Good conductors. Okay. Fourth point. Metals are solid. Metals are solid. Metals are solid. Exception para is liquid. Exception Hg. Para is liquid. Okay. Compounds containing covalent metals. Okay. Good conductors. And in fourth, compounds containing covalent bonds. Covalent bonds are solid, liquid, and gases. Okay. Fifth point. It is weak bond. It is weak bond. It is strong bond. It is strong bond. Sixth point. Metal possesses high value of conduction coordination number. Metal possesses high value of coordination number approx 8, 12 and 14. Otherwise, compounds containing in covalent bonds. Compound containing covalent bonds. Compound containing covalent bond possesses low value of coordination number. Possesses low value of coordination number. CN numbers. Okay, thank you. This chapter is in there, and next chapter is S block elements. Okay, we will be studying about S block elements. Thank you.